Well, welcome to question 2 at the end of chapter 12, Fundamentals of Particle Technology, and this is all about mixing powders. And the example here is where we have 3 powders that need to be mixed together, A, B and C, and they mixed in the proportion of 60% A, 30% B, 10% C by mass or by weight. Each powder consisting of mono-sized spherical particles, a little bit idealised, but never mind. The density is 2,600 kilograms per metre cubed for all the particles, but the diameters are different. They're 100 microns for particle A, 80 for particle B, and 50 for particle C. And we're told here to consider, for the purposes of our investigation, particle C as being the important one, so that's the 50 micron particles. The scale of scrutiny for this mixing process is 100 grams. There are 100 gram samples being taken from the mixer, and at 20 minutes the variation between, or the standard deviation between the samples of 100 grams each was this value. At 20 minutes, at 40 minutes it's this value, getting less, and at 60 minutes it's this value. So a certain number of samples has been taken. We're not told how many samples that is. They're all 100 grams in size, and according to the scale of scrutiny that should be the same mass as the final product for the process, but the variation or the standard deviation at the different times are given here. That's 20 minutes, 40 minutes, 60 minutes. And there's a very good question. Are we at the expected random mixing? Is there any point carrying on mixing for any further time? How do we estimate really the time required for the mixing? We have 3 sets of data, but is that enough? And then it mentions this confidence we have in the result and further experimentation. Okay, so it's a good practical problem. The way we're going to solve this problem is using Poole-Taylor and Wall's equation, which says that the variance of a mixture, and it's for a binary mixture, but we'll deal with that in a moment, is the mass proportion P times by Q all over the scale of scrutiny, the mass of the sample, and then quite simply the weight of the particle P, of one particle P, times by the proportion Q plus the weight of the other particle for a binary mixture, which we'll call Q, times by the proportion P. Fairly simple equation. Please look at the other video, the part 1 video, to see a discussion on this equation. But it's a nice simple equation. Now we're told that these are mono-sized particles, so we can do a bit of tidying up before we start to do any calculations, because if we're going to use the idea that they're mono-sized, and we use C as being, so component C as being WP, then we know that WP will be pi over 6 because it's a sphere, that's the volume shape factor, times by the density, okay, I'll just leave that as rho rather than rho s, times by the particle size, which we know is going to be 50 microns, but for the moment let's just call this xp to make it a little bit more general, and we need to cube that particle size, and that will give us the mass in grams if we're working in CGS units for WP. And likewise for WQ we can write down the fact that we still have the volume shape factor, we still have the density, but here we do know that we're going to have to take into account the mixture of the other 2 components. P was nice and simple, but here we have A plus B. We still want to calculate the average particle mass of these two combined. So the way we'll do that is we know that as far as A is concerned, it has 60 over 90. We're only going to 90 rather than 100% because we've got 10% of component C. We have 60% of component A and 30% of component B. So we're weighting these particle sizes according to the amount that's present. So for particle A, that will be 60 times by particle A cubed, and then for the particle B, that will be 30 over 90. So this is calculating the fractional contribution to the average particle size, and that will be xb cubed. Okay, well, we're more or less ready to put some numbers in, and again that will be in terms of grams. Okay, so let's put some numbers into our equation then. So we have our sigma r squared, the variance, and this is the expected variation at maximum randomness when we've achieved the best mixing possible. We know that P, the proportion of our component C, the one we're interested in, is 0.1. Therefore, we also know that Q is going to be equal to 0.9. We know that the sample mass is 100. Okay. WP is fairly straightforward because we have just the component C for WP. So I'm going to just leave that as x cubed, and in fact that's C, isn't it? Component C. And I'm going to take out the reason what I've done here is I've called that xp now xc because that's what it is. It's component C, and I'm taking out the pi over 6 and the density, and I'm going to put it on the right hand side because that's true for both WP and for WQ. So let's park pi over 6 and density for a moment, but we do have a slightly more complicated problem here because we need the weighted values of these. Well, 60 over 90 is 2/3, so that's 2/3 xa cubed plus 1/3 xb cubed, and then we need to take into account that we have pi over 6, which is true for all those sizes, so we can take that out, and we also have a density of 2600, which is 2.6 grams per centimetre cubed. So we're almost there. We've almost got the problem that we need to work out. All I need to do now is to expand the particle sizes, bearing in mind we're working in CGS, centimetre gram seconds, so we haven't changed anything there. That's nice and straightforward. But here we now have particle C, which is 50 microns cubed. Oh, I've missed out the Q and the P value, haven't I? Sorry about that, because we should have multiplied this by Q and this by P. So just slot those back in again down there. So Q is 0.9 times by the 50 microns, so that's going to be 50 times 10 to the minus 4 all cubed. In fact, I can take the 10 to the minus 4s out as well, because this will be a recurring theme for all all the sizes. So I've got a 10 to the minus 4 to take out and cube. And then we've got plus, I'll bring the 0.1 to the front here. That's the 0.1 for P. So then that is still 2/3 times by particle size A was 100. So that's 2/3 times by 100 cubed plus 1/3 times by 80 cubed. 80 cubed. Okay. And then that leaves us our pi over 6 times by 2.6 times by our 10 to the power minus 4, but that's got to be cubed, so that becomes 10 to the minus 12. 3 4s are 12. Phew, I could leave all these 10 to the 4s, 10 to the minus 4s in here for these different particle sizes, but if we do that, the numbers just become crazy. So it's quite straightforward to just simply take that out and call it 10 to the minus 12 there. Well, there's a lot of calculation to do, so clearly we're going to use Excel for this. So let's pop over to Excel. What I've done in Excel, I've set up the 4 separate components to the calculation. There's the initial PQ over M. Okay, so that's P, that's Q, and that's M. Then I've got the 50 cubed times by 0.9, which is the first term inside the square bracket. Then I've got the average particle mass term for the other 2 components, the components A and B. They're weighted by 2/3 for the particle size A, 1/3 for the particle size B, and then don't forget to multiply by the big capital P value, 0.1, and then we've got the bit that's stuck on the end of the equation, the pi over 6 times by 2.6, and the 10 to the minus 12. And all I've simply done is here, all I've done here is to do exactly what the equation says it should be, which is C2 times by C3 plus C4 times by C5. So it's just laying out the problem numbers from above. And that gives us a variance then of 2.4 times 10 to the minus 10 and a standard deviation of 1.55 times 10 to the minus 5. Right, so the question was asking us to comment on these values of standard deviations and how we can use that to calculate if we have reached an appropriate time for mixing, if we've reached what we would expect the mixture quality to be at maximum randomness, because we know we're not going to get a perfect mix. Okay, well how are we going to assess that? Well, we're going to assess what we are expecting from the pool equation, which we have here. I've just brought the numbers over, 2.4 and 1.55. Okay, so that's 2.4, 1.55. And then the new values that are just here have come in from the question itself. So the 20-minute, 40-minute, 60-minute standard deviations. From the standard deviations, we've calculated the variances. So we've just squared the standard deviations and then taken log to the base 10 of the variances. And then the graph that's plotted here is a graph of the log to the base 10 of the variances against time. Okay, and you can see that it's pretty close to being a straight line, not a perfect straight line by any means, but it's not far off a straight line. And I also have the Poole, Taylor and Wall values again plotted as the variances, log to the base 10 of the variances against time. So here are our two sets of data. The first data in blue being the experimental data, the data in a sort of browny orange colour being the theoretical. So Poole, Taylor and Wall is telling us what we should expect when we've got maximum randomness for these particles. It's a very low standard deviation and variance, but we've not got there. At 60 minutes we're still a little bit off, maybe certainly more than an order of magnitude off on the variance, and if we extrapolate we could make a case that the mixing needs to carry on for maybe 80 or 90 minutes. So if all else, if nothing changes in terms of what's going on during the mixing, we would estimate that really we need a 90-minute mixing time to get to the at best mixing. It's not, we're never going to go below this value, or at least not theoretically we're not going to go below this value, but we hope to be able to get to this value. So that's suggesting a 90-minute mixing time. So we haven't mixed for long enough. However, we could find actually that we get segregation taking place. The Poole, Taylor and Wall equation isn't going to tell us an awful lot about segregation, so we might actually end up with the mixture quality getting worse. So it would be worth actually running the tests up until the 90 minutes just to confirm that segregation isn't a major issue with this material. It's unlikely to, because the densities are identical, they're spherical particles, and the sizes, the particle sizes, don't vary that much. From 50 to 100 microns, that's not a huge variation. So the indications are that there shouldn't be a great deal of segregation. The one last phrase that was used though is, what do we mean by confidence? Well, we've obtained the variance from the Poole equation, and from that we can obtain the standard deviation. It's the square root of the variance. And if we take the 99.8% confidence thresholds, then 99.8% of the distribution will be plus or minus 3 times the standard deviation. So 3 times 1.55 is still a very small number. It's only 4.5 times 10 to the minus 5. Okay, well the mean value is 0.1. You know, we're expecting component C to be 10% of our mixture, or 0.1. So the variation on component C at 99.8% confidence limits is 0.11 plus or minus 4.5 times 10 to the minus 5. That is very, very tight. It is very, very close to 0.1. So you could actually go up to a much higher degree of confidence, 99.99 something, before you get to a significant removal from 0.1. We are pretty confident that this should be a good mixture, and that's again logical because we've got spherical particles, we have a 100 gram sample and a 100 gram product. That's actually quite a lot, bearing in mind that in Poole's equation the mass is at the bottom here, so having 100 grams is going to give us a relatively small variation, and we actually have particle sizes that are only varying between 100 to 50 microns, all at the same density. So it's not too surprising that it's predicting a good mixture quality. Okay, so is further experimentation necessary? Yes, because we're at 60 minutes and we're anticipating that we might need 90 minutes. So it's worth doing just to check something hasn't happened with the segregation. So it's worth doing that. We just need to take it to 90 minutes. And what sort of confidence do we have in the mixture quality? Well, we've got fantastic confidence in the mixture quality because the variance is so low. Okay, please do have a look at question 3, which expands a little bit on our weights. It uses the size distribution to calculate the weights of the particles rather than just calling something monosized as we did here. Okay, thank you. Bye.